Okay, welcome back. So today we're going to be taking some of the ideas that we have been talking about for the last few lectures and putting them together for a very important topic. This brings us to section 20, which is entitled Electric Circuits. Okay, now the things we're going to be talking about today are some very general ideas in electric circuits that basically apply to all kinds of circuits. Although it might be a little bit hard to see how these things work in some things like microcircuits or something like that, the basic ideas are really still the same. The thing that makes electric circuits do anything is the fact that there is current going on in them. There are moving charges. So, we start with moving charges. In order to move the charges, we have to have some force acting on them. Well, a force that moves electric charges is basically, we know, an electric field. Anytime we have an electric field being applied over two different positions, we can define a potential difference between those. So rather than talking about the electric field, we will really typically talk about the potential or voltage between 2 points. So that's what we're going to use. We're going to talk about the voltage within a circuit as opposed to either the electric field or the force or something like that. All right. The object that actually creates a voltage we will think of as some kind of power source. So our power source will be what creates a voltage difference between 2 points in our circuit. The symbol that we'll use when we want to draw a circuit will look something like this. So this will be our power source, the symbol that we'll use for our power source. And we'll typically assume that there is some potential difference V from one side to the other. Now the symbol is two parallel lines, one longer than the other. Now be careful when you draw this, make sure that one is longer than the other, because if you draw them the same length, that's actually the symbol for a capacitor. So we're not talking about capacitors right now. So one longer than the other, that will be our symbol for a battery or a power source or something like that, some source of voltage. The long side we will assume to be at the higher potential. The short side will have that for the lower potential. So this will be the positive side, this will be the negative side. Okay. Now, any kind of battery or anything like that that you buy will always tell you what the voltage is for that battery. So let me just show you some examples. Okay, so for example, here is a regular D cell, and if you look at the D cell right here, it says 1.5 volts. So what that's telling you is that the potential difference between there's the positive terminal here and the negative terminal is 1.5 volts. Here is a C cell, and if we look at the C cell, somewhere on here, there is it, there we go. Again, it says 1.5 volts, and there's the positive terminal here, negative terminal back here. Even this kind of battery, what kind is this? Well, this is what we call a 9-volt battery, because the terminals are 9 volts from one to the other. And if you look very carefully, you can see this. Where does it say? Oh, there it is. So on the side it says positive, so that's the positive terminal, that's the negative terminal. And the potential difference between the ends is 9 volts. Even these little tiny ones here, some hearing aid batteries. So here are the batteries, two different sides will be the two different terminals, top and bottom, and on the back here it says the difference is 1.4 volts. So a volt is the unit of potential difference, and the potential difference between the two terminals on the battery is always going to be given. All right. Now we can think of the voltage of a battery kind of like the pressure in a water pump. The voltage is what pushes the current, actually in this case, pushes the current through the circuit, kind of like we might have a some kind of water pump or here that's turning around, pushing water through a water pipe one way, drawing in the water the other way, and the water pump has got some kind of pressure. The more pressure, the more it's pushing on the water, the more it's pulling in the other way. Well, the higher the voltage of the battery, the more it's pushing on the current through the circuit one way, pulling the current in the other side on the other way. The voltage of a battery is sometimes referred to as the battery's electromotive force, or the EMF of the battery. Sometimes we'll write this just as a script E for the electromotive force of the battery. The terminal voltage, actually the voltage at the ends of the battery, is a little bit different than the EMF. Batteries typically have what's called an internal resistance, and so the more current they actually are trying to put out, the lower the voltage. So when you have a load on the battery, it actually decreases the terminal voltage. But I'm afraid we're just not going to have time to worry about that, so we'll basically assume that the EMF of the battery is the same as what the voltage is at the terminals of the battery. We'll use those synonymously. Okay, so what we know is this voltage of the battery pushes on the current, makes the charges move. So what do we mean when we're talking about the current? Well, let's imagine we have a wire. So here's kind of a blown up view of the wire. And we're going to imagine something very simplistic. Imagine we've got these charges in the wire, and these charges are moving through the wire. Now actually, real current is a lot more complicated than this. These charges are moving around, bumping into other atoms and molecules, things like that. We're not going to worry about that. We're just assuming we've got some charges. These charges are moving through the wire. Now imagine we set up like a little window here, or a little doorway, and we stand here and we watch how much charge passes through this cross section of the wire per time. How much charge per time? So imagine we've got some amount of charge, we'll call it delta Q, that passes in some time delta T. Well, the ratio of delta Q over delta T, that's how we will define the amount of current. So the more charge that goes through, the higher the current. In a shorter time, in other words, if it's moving faster, the more current. So the current we will define as the charge flowing through the wire per time. And the symbol that we will use for this will be a capital letter I. Now the units of I for current will then be the unit of charge divided by the unit of time. But what are the units of charge? Well, those are coulombs. What are the units of time? Seconds. Well, that's a combination of units that we will see often enough that it has got its own name. And 1 coulomb per second is defined as 1 ampere. Or 1 amp for short, or just 1 capital A for even shorter. So the units that we will use for current will be amps, and the symbol is just going to be a capital A. But keep in mind, what that means is 1 amp means 1 coulomb of charge passing through the wire every second. 1 coulomb per second. Okay. Now, this might seem a little odd, but our definition of current will be in the direction that positive charges are moving. So we'll assume, for the moment, that the actual charges that are moving through the wire are positive charges. The direction that the positive charges move, that will be the direction that we will define as the current. On the other hand, if current is actually made by the motion of negative charges, like electrons, they would actually move in the opposite direction. So if you apply an electric field, electrons will move one way, positive charges would move the other way. Well, the motion, or the actual physical velocity direction of the electrons, will be in the opposite direction that we will use for the current. So, keep in mind, if we have a battery, remember the long side is the positive side, the short side is the negative side. Now, what would a positive charge do? If we had a positive charge here, how would that positive charge move? Well, it would be repelled by the positive side, attracted to the negative side, so a positive charge would move in that direction. So that's the direction we will define as the direction of the current. So current, in this case, will go in a clockwise direction with that orientation of our battery. What would a negative charge do? If we had a negative charge, if we had a negative charge here, a negative charge would be repelled by the negative side, attracted to the positive side, so an electron would actually move in a counterclockwise direction. So, let's keep in mind, when we talk about the direction of the current, we're talking about the direction that a positive charge would go, opposite the direction that a negative charge would go. Okay? So, a general thing to keep in mind is, current goes from positive to negative. In other words, from high potential to low potential. What does water do? Does water flow uphill or downhill? Water flows downhill. Current goes downhill. Electric current goes downhill from high potential to low potential. So just keep that in mind. Current goes downhill. Okay. Now, there are actually two kinds of current, two kinds of circuits that we will talk about. There is DC circuits. DC stands for direct current, while AC stands for alternating current. So a DC circuit is one where the voltage is essentially constant, pushing in one direction, and essentially for our purposes, for the time being anyways, we basically have a constant current, a current constantly going in one direction. An AC voltage source is one that pushes one way and then pushes the other way, pushes back and forth and back and forth. So the current will actually go first one way, then another way. Then the first way, second way. So the current actually sloshes back and forth. The symbol that we'll use for an AC voltage source is like a little sine wave. So imagine we had a circuit with an AC voltage source. We would get current first going one way, pushing one way with one side, the high side, and the other side, the low side. And then sinusoidally it would switch, and we would have our voltages switched, and now our current would go in the opposite direction. So we'd have the current sloshing back and forth and back and forth. We'll come back and talk more about AC circuits later on, and a whole lot more after a few lectures. Okay, so back to DC circuits just for the moment. Let's imagine that we have, again, a voltage source in some kind of circuit, so connected in some circuit. We have some applied voltage V. We have a current I. Now, the work of a physicist who was working on these circuits by the name of George Simon Ohm, who lived from 1789 to 1854, he noticed that if you increase the voltage, what would you expect? If you increase the voltage, what do you expect from the current? You expect the current to increase. The greater the voltage, the greater the current. If you decrease the voltage, you expect to decrease the current. Well, he wrote this as a proportionality, such that V was proportional to I. But what's this proportionality constant? Well, he noticed that if you had a short wire, you got a lot of current. But if you had a much longer wire, you got less current. So there was something about the wire that could affect the amount of current. He called that, or we will call that, the resistance. the resistance of the wire, or the resistance of the whatever is in the circuit. Okay, this result is what we will now refer to as Ohm's law. So that is Ohm's law. This is a very important result. Okay, I want everyone to repeat this with me. It is a very important result. Why is this a very important result? It is a very important result. V equals Ri. If you can remember that this is a very important result, you will remember Ohm's law, because it is very important. V equals Ri, very important. Okay. You'll always remember what it is. It's not Vi equals R or something like that. Very, V-E-R-I. Okay. R is what we will then call the resistance of whatever this is. Now, so R measures how much the circuit resists the flow of current. So we can kind of think of this going back to our water analogy. Imagine we've got, say, a water pump here. Somehow pumping water out one end. And we've got this connected up. Now imagine we've got something stuck in the water pipe. Somebody's been washing their hair or something like that. We've got a clog in the pipe. The clog resists the flow of water around this water circuit. The more cloggy, so to speak, this is, the more it's going to resist the current. The more resistive this is, the less current we get. The less resistive it is, the easier it is for current to go through, the more current we get. Well, that's exactly what's going on here. The larger R, the more resistive our circuit, the less current we're going to get. The less resistive the circuit, the smaller R, the more current that we'll get. So it kind of makes sense. It makes qualitative sense. The units that we will use for R will be equal to the units of V divided by the units of I, which are, the units of V are volts, the units of I are amps, and so the units of resistance will be a volt per amp. And again, this is a combination of units that we will see so often that it's got its own name. 1 volt per amp is called an ohm, named after you-know-who. The symbol that we will use for this is a capital Greek letter omega. So ohm, omega. Okay, so that's the symbol that we'll use for resistance, ohms. Ohms of resistance. So let's stick some numbers in here.